So on this last session, I would like to welcome Dr. Nta Methha Sawat from National Electronics and Computer Technology Center to give a lecture on the topic of Introduction to Terahertz Imaging Applications and Perspective in Thailand.
So, first of all, good morning, everyone. And I would like to thank TAPE Center to give me opportunity to be here. So today I'm gonna present about the terahertz technology and how we use such technology to create images. And I'm gonna talk about the potential applications and perspectives of terahertz imaging in Thailand. So, as you guys have already seen from the previous presentation, I'm not sure why it doesn't work right now. Okay, so, all right, it works, right? Okay. So terahertz is just another kind of electromagnetic waves that has a frequency in the order of 10 to the power of 12 hertz, or approximately 1000 gigahertz. So even though terahertz signals are very challenging to generate, they still have some interesting properties that are worth looking at. So the first property is that it has the ability to penetrate through non-polar materials, for example, clothes, papers, woods, and plastics. And the second property is that terahertz signals are quite sensitive to water and other polar materials, so meaning that you can do some moisture imaging experiments. So terahertz signals are reflected by metals just like X-rays, but on the other hand, X-ray is ionizing. That means it's dangerous to human body. If you compare with terahertz signals, terahertz signals are much safer to human body and living lives. And last but not least, most importantly, terahertz signals can be used to identify biomolecular interactions that can be done by terahertz spectroscopies. That I'll talk about that later on. So if we are talking physics right now, we are comparing terahertz with other kinds of electromagnetic waves in terms of their frequencies. If you compare terahertz and infrared and visible lights that have higher frequency, you can see that terahertz has lower frequency than those. That's why it has better penetration. And if you compare terahertz with X-ray, then obviously it's safer to human compared to X-ray. And if you compare terahertz that has higher frequency than microwave, then you have the better image resolution technically. So with that said, you have so many interesting potential applications for terahertz, and you have different applications in different areas. So let me give you some examples on that. So first of all, in the food and agricultural sections, you can do, for example, moisture imaging to determine the hydration level within the plants. So you cannot see by your naked eyes whether the plants are dehydrated, but you can see the hydration level through the terahertz images. You can also see the suspicious items inside your food product. So here shows an example of the sugar that has the meatworm hidden inside. You can see it through the terahertz image. And this is another comparison showing that, okay, there's no meatworm in here. So you see the difference between these two images. You can also use the terahertz signal to figure out the infection stage. You can see whether your seeds are infected by mycotoxin or are germinated by the germs, or let's say if you have the wheat product, you can figure out the body stage of your product as well. So these are some cool applications for the food and agricultural products. In industrial applications, you can use terahertz signals to image the internal structures of, for example, in the tire, you can see whether the structure inside the tire are in the good condition. And you can also use terahertz instead of X-ray to image the internal structure within the electronic components because terahertz is safer, also safer than X-ray for electronics. For security application, you can use terahertz just like X-ray to kind of screening for hidden weapons at the airport, or you can use it to screen the hidden items in, let's say, luggages or in your parcels at the postal office, for example. For pharmaceutical application, you can use it to figure out which drug is the authentic one and which drug is fake one. The reason that I'm calling authentic and fake is because both types of drugs are made from molecules that have the same molecular formula. So I think they call it isomorphism. But even though they have the same molecular formula, they have different structures. So terahertz can identify both molecules that are isomer to each other. So depending on type of the structure, it gives you different signals. So you can use these differences to figure out which one is the true authentic drug that is more effective than the fake drugs. And you can also use the terahertz imaging to do the quality control to figure out the uniformity on the surface of the drugs so that you can see whether it's uniform enough based on the signal that you receive from your system. And in terms of medical application, you can use it to screen for the cancer because cancer tends to absorb the terahertz signals differently compared to the normal tissue. So you can figure out those differences. Also, you can use the terahertz to figure out, to image the level of mineralization within the tooth and especially in enamel level. And you can also see the cavity in the center of the tooth as well. And this is my favorite though. So this is a system that can see whether you have the diabetes from the food itself. So let's say the person who is having diabetes, they tend to have less water content on the food. And if you compare the water level of the diabetics and the control cases, they have different level of waters in the food. So that's how they can figure out the diabetes in the patients. So now that I've talked about different applications that could be potential applications in Thailand, so let me talk about perspectives. And these perspectives are in terms of the imaging techniques that I think are interesting and are the most feasible in Thailand. Of course, there are so many imaging techniques available out there, but these are some of the most interesting ones. So let's see what they are. So the first thing first, the very simple imaging setup is done by just having the simple transmission imaging. So you have the source that emits the terahertz signal, and the terahertz signal passes through the sample here that is close to the camera. And the remaining signal after passing through the sample will get hit on the camera. And that's how you detect and create the image. So this image, let me emphasize that it's just the image that represents the projection image of a given sample. So imagine that the projection image is just like a shadow of the object of interest. And here are some examples. You can see that the knife has different materials. It consists of the steel and also plastic, and they have different absorption levels. So that's why it produces kind of contrast in the image. And also, you can, of course, do some other kinds of imaging, and then you can see different appearance here. So this system is very simple, but it turns out to be very effective to do the screening inline. And we also have this kind of system as well in our lab to show to the guests, and when they come and they want to learn more about the how terahertz technology works, so we always show this kind of system to them. We can see that the terahertz image allows you to show the image of the hidden object inside the package. And also, like I said, it's sensitive to water, so that's why it shows where the moisture content is as well. But you cannot see both of them in the naked eyes. You cannot just see them from the camera, from images from the camera. But although you cannot see them, you can still see their colors. So that's why we think, okay, why don't we just add another webcam to provide you the visible typical image, and also you also have the terahertz image, and you can combine them to have both external and internal information in the single image. So that's what we have done. But like I said, this simple terahertz transmission only gives you the projection of image of the object. So what about if you want to create the image of the cross section of the object that you have? So for example, if I'm going to the hospital and I want to have the image that represents my cross-section image of my internal body. So how do I do that? I couldn't do it using this simple terahertz transmission technique, right? So that's how we have another technique. So this is called terahertz computed tomography. So this concept, computed tomography or CT, has been already used in other imaging modalities like X-ray, photon imaging, and ultrasound imaging. We have done that. So that's why there are some groups that have done this on terahertz as well. So the concept of CT or computed tomography is you collect the projection image at multiple angles, and then you collect all those projection images and combine them into a single piece of data that's called sinogram. And then you apply the image processing. That could be, for example, filtered back projection, iterative algorithm, to get the image representing cross-section of internal structures. So that's how you do the computed tomography, and that applies to all the imaging modalities out there. Intuitively, if you increase the number of projections, I mean the number of times you acquire the projection images, likely you will have the better image quality, right? Because you have more data. But this will apply only up to a point. That means if you keep increasing, it's not gonna give you better image resolution anymore. So it has some limit. The reason that you have some limit is because the terahertz signals are more prone to scattering and diffraction and refraction as compared to X-rays. So if you see these images, even though it can show you some internal structures, you can see there are some artifacts in there. And so as here as well. So this shows the image of the bone that are correlated well with X-ray image. But it seems to have more artifacts. And the resolution is poorer because the artifacts blur the image. So that's the reason why we have another idea to do the CT scan based on the knowledge of the full wave propagation. So what does it mean? So let's say if we have the image that has different levels of refractive index. So I am sure all of you know that the refractive index will change the way that the wave propagates, depending on the value of refractive index. So here, if you have different refractive index, then you will have different patterns of the waveform. And if you measure the intensity of the waveform at the receivers that are represented by the dots here, and then you take all intensity measurements to do the reconstruction, then conceptually you should get the image, and that's what we have done. So we have taken all the intensity measurements at the receiver and do the nonlinear inversion of these equations. So and doing this way, we get the reconstructed image. And like I said, this is not a typical CT reconstruction because this gives you the distribution of the refractive index image. Before that, we assume that the refractive index doesn't change, right? We assume that the refractive index is equal at all area within the image. But this one doesn't need that assumption. Okay. I have to emphasize that we have done this collaboration with Mahidol University too. They help us a lot in modeling the wave propagation using these complex equations. Another kind of terahertz imaging is, let's say you have the samples that are very absorbing and scattering, that the signals cannot penetrate through at all. That way, you cannot do transmission imaging. You have to do reflection imaging. So reflection imaging is done by having terahertz signals penetrating within the sample surface a bit, and then the signals get reflected to the detector. This is very useful, and I'm not sure if any of you have seen this news before back in maybe 6 or 7 years ago. So here's the headlines of the news. So it says that the MIT team has used the terahertz reflection imaging approach to actually read the books within the first 9 pages, and they did not open that book at all. Okay, so the way that they did that is they sent the pulses, of course terahertz pulses, through the ancient book, and they received the return signals in a pattern like this, and they applied the signal, some kind of signal processing to kind of extract the information on each page, and those information are the letters on each page, and they could do it up to the first 9 pages. I think the limitation would be the high scattering itself. So they couldn't go further beyond 9 pages. But that's something very cool that we can consider as well if you do some imaging. We have also done that, even though it's not on par with that, but we did something that utilizes the reflection approach too. So we have the stage here that can turn the sample, and we have the emitter that sends the terahertz signal, and once the signal gets reflected here, it is reflected back to the terahertz detector. And when you turn the sample around using the motor, you can create kind of the panoramic view of the object, 360 degrees view. And then you also have another 3D camera that captures the 3D surface information of the object. Now that you have the internal information from terahertz and outer surface information from 3D camera, you can fuse them to kind of have the 3D model representing both outside and inside information. Another one is the terahertz phase imaging. So like what you have seen from the previous presentation, if you have the time domain signal, of course you can extract the phase in addition to amplitude. The reason that phase is very interesting is because first of all, you can see that if you compare, okay, this is the amplitude, this is the image reconstructed from the amplitude, and this is the image, another image reconstructed from the phase, amplitude phase. You can see that they are complementary to each other, right? So you can use that as the additional information. That's one of the interesting things. And the second one, phase, is less sensitive to the signal loss. So meaning that if the signal power is lost somehow, then you technically you still get the same phase. So it's insensitive to the power loss. But the drawback is that it usually requires the time domain terahertz signal. So that's why we'd like to advertise here that we have the facility at NECTEC to acquire the terahertz time domain signal. We have 2 systems so far. The first one is quite the commercial one that can do the signal acquisition very fast. And the second one is the customizable version of the TDS system. And I have to say that we are also working with Ajahn Sakhon at Chiang Mai University to build the benchtop of the TDS system based on the experiments on this system too, and also the components on this system too. So these are the time domain spectroscopy systems. But let me tie in what we also have as well. So we also have the FTIR system, even though it doesn't give you the time domain signal. But like I said, this one is quite the flagship model of FTIR. So if anybody has any idea or would like to use it, feel free to contact us, and we are happy to assist or discuss with you further regarding this. Last but not least, sorry. So this one is the way to work towards getting higher image resolution. Well, if you do some imaging, most of the times you are prone to the blurring effects, and those blurring effects are due to the optical components. So think about if you have magnification of lens, you get blurring effects, things like that. And we kind of we say that those blurring effects modeled as the point spread function. You could think about that way. So the point spread function, mathematically, it can be modeled as the convolutional filter. So if you have the image and you apply convolution filter, you get the blurry image. So the convolution tries to model the point spread function of the optical components, and you reverse the convolutional process by doing the deconvolution process to recover the original image. So this is the original low resolution image. If you know point spread function, you do deconvolution and then you get the high resolution image. Okay, that's the way to improve the resolution of the image. Another technique that we would like to try, but we haven't got the equipment yet. So if anybody has equipment, feel free to try on our setup too. So this is the technique called compressed sensing. So the concept of compressed sensing is that it tries to reconstruct the high resolution image under the constraint that your measurements are so limited. So let me give you some example of how that works. If you want to create two-dimensional image from the single pixel detector, you have to scan pixel by pixel until you have acquired the data for all the pixels, right? And that takes a lot of time because you have to raster scan every pixel. Now, compressed sensing takes different approach. You have, instead of taking each pixel until you complete all the area, you just have another device called digital micromirror device or DMD. So DMD here consists of an array of tiny micromirrors that can turn on and off depending on the pattern. So for each randomization pattern of the DMD, you take one measurement and you randomize the pattern of DMD for a small number of times, and you have a small number of measurements. Believe it or not, just a small number of measurements allow you to reconstruct the image that is very similar to the full version from the full measurement. And that is done by the clever way of mathematic algorithm reconstruction. So this is you have only 35% measurement compared to the conventional acquisition. This is what you get. If you have 75% measurement, then this is what you have. So you can see that even though you decrease the measurements a lot, you still get the image that is comparable to the one obtained from higher number of measurements. But the easiest way to get the higher image resolution is to have the higher frequency. I would like to use this opportunity to advertise a bit as well that we also have the quantum cascaded laser QCL that acts as the terahertz source for doing high resolution imaging. We also have the parameter that is calibrated to have the correct readout. Okay, and the frequency that we have is tunable from 1.6 to 4.3 terahertz, and the output power could be up to 20 megawatts. So feel free to use it or feel free to discuss with us if you have any other ideas. All right, I think that's it. And sorry that I'm running out of time a little bit. Thanks for your attention. If you have any other questions, feel free to ask me right now or discuss with me later. Thank you.
Thank you, Dr. Rungroj, very much for the lecture. Is anyone have any question?
Thanks a lot for really interesting talks. I have a question about the inverse design that you use to recover the terahertz image. You say it's non-linear inversion. Could you elaborate a bit what is this?
Yeah, sure. So the reason that it's nonlinear is because of the Maxwell's equation by itself. So the way that we try to reconstruct the image here is not just you feed the input and then get the output image in one turn. It's not like that. So we have to do the iterative optimization. So what does it mean by iterative optimization here? So it means that we have the algorithm that tries to seek for the best reconstructed image. So, and also the next question is, what is the best reconstructed image? The best reconstructed image should give you the corresponding wave propagation pattern that is closest to what you measure. So if you get the wrong image, then the corresponding simulated wave propagation pattern will not be similar to what you actually measured. So that's the concept idea. Now, the reason that it's nonlinear is because there can be so many answers that gives you the same wave propagation pattern. And that makes it very challenging to get the solution that is correct. So that's why the problem here is very interesting in the research field.
So you model this for all different illuminations and check for all the pattern that generate from the sample.
I'm sorry, I couldn't hear the question.
So
sorry.
basically in CT you need to illuminate in different projective, right?
Right.
And with that means you need to model all of them to get the final outcome.
You mean in typical CT, right?
Yeah, in typical CT.
In typical CT, I guess it's based on X-ray or PET or SPECT that somehow they have diffraction, but it's so less that in most of the cases you can ignore them and you can just do like this. So here is the simplest form of the reconstruction. You assume that the propagation of the wave is always straight. It doesn't change the direction at all. And by this assumption, you can really simplify your reconstruction approach. But in here, what we are doing is different. So the wave can change direction. And by changing direction alone, it really complicates the reconstruction algorithm. Did I answer your question?
I need more detail, but I think we can discuss it later.
Yeah, sure.
Okay, thanks.
Thank you. Thank you for the question. Any other question?
Have you applied terahertz on agricultural product with a high moisture content? Food and vegetable.
We have tried, but it didn't work quite well. We tried it before. So here is the inline everything setup that we have. So we try to figure out the moisture content in terms of percentage in the cracker. So what we tried to do is we collected the intensity signals from different pieces of crackers with different levels of moistures, and we constructed the calibration curve. So the calibration curve that we obtained from acquiring, different signals, different samples. These calibration curves represents the relationship between the intensity that you measure with respect to the moisture level. And the next time when you have a new sample, you measure the intensity, then you can also solve for the moisture percentage. That's how you measure the moisture content in the sample. But the reason that I'm saying that it's not good is because the sample itself are very inhomogeneous and the thickness are not uniform too. So that's why we have a high variation in our measurements and the predictions are not that accurate. Did I answer your question, Tom? Thank you. Any other questions?
Maybe we can discuss after or maybe during lunch because at 1 p.m. we will have the opening ceremony for the ICREM conference. And I'd like to thank all speakers and audience that made this event from the instrument side and the user to get closer and hope that we can organize this visiting to the narrow topic so that we may be able to see the possibility of access this instrument and also the user. Okay, thank you very much all, and we have the lunch at first floor. Okay, thank you.